Okay, so let me go through these notes on the limits to infinity. That's how we're going to end this unit on limits and continuity. So you always want to remember that limits to infinity describes the end behavior of a function on an infinite interval. So if you were to look at the graph of a function, we're finding out what is happening as x is approaching negative infinity and x is approaching infinity. So the limits to infinity is not talking about anything that's happening in the middle of the function as x goes from left to right. On the left end, the limit as x approaches negative infinity, and on the right end as x approaches infinity. So you've learned a lot about functions, and so there's some functions that you know just by the equation, you know what the end behavior is. Like, for example, a quadratic function that has a positive a value, you know it's going up on both ends, and so the limit as x goes to both negative infinity and positive infinity would be infinity. That's different than a limit as x approaches a constant value, because that's not the end behavior. So for this first function, it's a rational function. And if you put it in your calculator, adjust your window so you've got a nice view of it. If you want to complete the table, the values that are constants, you could either substitute them in algebraically, or if your window is set so that your x-min and x-max go to at least negative 100 and positive 100, then you could do second trace value and just type in the different x values, and you can get these output values. But what you want to notice is on this graph, you should notice that as x is going to negative infinity, so on the left, the function seems to be approaching the x-axis, and the same thing seems to be happening as x approaches infinity on the right, that it seems to be approaching the x-axis. So we would say the end behavior of the function as x approaches either positive or negative infinity, it approaches a function value of 0, which is what the limit is. All right, so if we change this function slightly and we square the x in the numerator, and again, put it in your calculator, adjust your window, you can notice that the values for the inputs are the same. And again, if you want to manually, algebraically substitute in these x values, you'll get these output values, or if your window is set so you have an x-min of at least negative 100 and x-max of at least 100, then you could do second trace value and get those as well. But what you want to notice is what's happening as x approaches negative infinity on the left side, and as x approaches infinity on the right side, it seems to be approaching a height of 3. So the limit as x approaches both positive infinity and negative infinity would be 3. So if you look at the graphs of both functions, it should appear that the end behavior of these functions approach a horizontal asymptote. So the asymptote guides the end behavior of the function. So like we've done the limits so far, we've had unbounded behavior, and that was related to vertical asymptotes. So here our end behavior will be guided by a horizontal asymptote if there is one for that particular function. So the line y equals L is a horizontal asymptote of the graph of f if the right-hand limit, the limit as x approaches infinity of the function, is that value of the horizontal asymptote, and or the limit as x approaches negative infinity of this function is that value of that horizontal asymptote. Okay, these are just representative of what we have with those first two functions, where we had in the first function, we had a degree of 1 over a degree of 2. In the second function, we had a degree of 2 over a degree of 2. All right, so keep going. Now we're going to up the degree on x in the numerator and try again. What you should see this time is the values are pretty different, and you probably don't notice any kind of a horizontal asymptote showing up. You should notice that on the left of the function, it seems to be going down to negative infinity, and on the right side of the function, y seems to be going up to infinity. So for this function, either approaching positive or negative infinity, the function value increases or decreases without bound, heading towards positive and negative infinity. That's called unbounded, and it's not the same thing as what we had with the vertical asymptotes, because this is separate from those limits. This is limits to infinity, which is only about end behavior. This behavior is unbounded, does not approach a horizontal asymptote. Many functions do not approach a finite limit as x increases or decreases without bound. So some of those types of functions, polynomials exclusively have end behavior where on the left they're either going to negative infinity or positive infinity, and same as x approaches infinity. Exponential functions, there's a horizontal asymptote, and so one limit to infinity, either to negative infinity or infinity, will approach the horizontal asymptote, but the other side goes to either infinity or negative infinity. So you can kind of just think through. We've seen the rational functions, and so this is an example of a rational function that has unbounded end behavior. So if y increases or decreases without bound as x approaches positive or negative infinity, then the limit as x goes to infinity of the function would either be positive infinity or negative infinity, and the limit as x approaches negative infinity of the function will either be positive infinity or negative infinity. A limit to infinity will not be plus or minus infinity, right? It can't go up to infinity and down to negative infinity at the same time on the same end of the same function. All right, so sine x and then also cosine x, because they have very similar behavior. They oscillate between a positive and negative 1, that's the maximum and the minimum, without bound. So when you're trying to find the end behavior, it never settles towards just going up to infinity or just going down to negative infinity or just approaching any one value. It just keeps that pattern what's going to continue and never settle on, one direction. So a limit to infinity for sine x and likewise cosine x doesn't exist. Of course, if I want to find a limit as x approaches a finite number, some other angle for both sine x or cosine x, there will be a limit, but the limit to infinity, it never settles on just one direction. It keeps that same pattern of oscillating. All right, we saw this with our other limits. The limit as x approaches 0 of sine x over x, and that was 1. How does it work when it's a limit to infinity? Now this function oscillates, but as x increases or decreases without bound, the function gets closer and closer to 0 from both the right and the left. So you're going to have to keep these straight now. The limit as x approaches 0 of sine x over x is 1, but the end behavior of that function is 0. So the limit as x approaches either positive infinity or negative infinity of that same sine x over x function is 0. If it's an end behavior limit to infinity of either sine x or cosine x, that limit does not exist. Whereas if x is approaching some finite value, there will be a limit. All right, so here is one more example. So we have, this is the same function. It's just repeated the limit as x approaches infinity and then the limit as x approaches negative infinity. So it's not two separate functions. So it says graph both of these functions, but it's the same function. We're just looking at what's happening as x goes to negative infinity versus x goes to infinity. Okay, so what happens is if you look on the right side of the function, it seems to be approaching a different height than it is on the left side of the function. And that height, that horizontal asymptote it seems to be approaching on the right is 3/2, but on the left it seems to be negative 3/2. You'll see on the right side of the function it's above the x-axis, and on the left side it's below. So the limit, what you want to do in this case is you can't actually take the square root of the quantity 4x squared plus 1, but what you're going to do, because we just care about end behavior, and so the plus 1 part of that denominator is does not enter into the end behavior conversation. So for that reason, we can just ignore it while we're finding the end behavior limit. We can simplify the square root of just the 4x squared to either plus 2x or minus 2x. Okay, the square root of just the 4x squared, because that's the only part of that denominator that's going to affect what's happening as the end behavior. The plus 1, it obviously has some impact to that function in that graph, but if I change that plus 1 to a minus 1 or the plus 1 to a plus 3, it's not going to change the end behavior of this function. The only thing driving the end behavior of this function in the denominator is the square root of 4x squared. So I can just isolate that, simplify that square root of 4x squared to 2x, and then we're going to, if x is approaching infinity, we're going to use the plus 2x. If x is approaching negative infinity, we're going to use the minus 2x. And that's how we're getting two different limits for x approaching negative infinity and x approaching infinity. Okay, so here's your rules. I refer to them just for memory purposes and simplicity of referring to them, like as in showing your work, as rule 1, rule 2, and rule 3. When you go to calculus, you still need to know what the rule is, but in terms of showing work for limits to infinity, most cases there's not a lot of work to show. And so you can just say, I used rule 1. So it's rule number 1, rule number 2, rule number 3. Sometimes there will be a little work to show as well, but that gives me something to check. So if your answer's wrong, I can say, okay, well, they knew it was a rule number 1, but they just wrote the wrong answer down. So what is rule number 1? This works for the limit as x approaches either positive infinity or negative infinity. It's about the degree of the numerator versus the degree of the denominator. Remember, the degree, thinking polynomials, is just the highest exponent if it is not factored. If it is factored, you'd have to count up all the x's, including related exponents, just like with polynomials. Okay. So if the degree of the numerator, in this case, the degree of the numerator is 1, x to the first power, is less than the degree of the denominator is 2, because we have x squared. So if the degree of the numerator is less than the degree of the denominator, then the end behavior approaches a horizontal asymptote of y equals 0. Therefore, the limit as x approaches either positive infinity or negative infinity of this type of function is 0. We'll see some examples here in a minute. Then rule 2, now the degree of the numerator is the same as the degree of the denominator. And if that's the case, you just isolate the terms that are determining the degree from the top and the degree from the bottom, and you just reduce it. So if I take 3x squared over x squared and simplify that, it just simplifies to 3. So you take the coefficient of the numerator divided by the coefficient of the denominator. That will be where that horizontal asymptote exists, and that will also give you your limit to either positive infinity or negative infinity for that function. So for this one, I would say the limit as x approaches infinity for this function equals 3. The limit as x approaches negative infinity for this function equals negative 3. Rule 3, that's where it's going to be just a little more complicated. So this is if the degree of the numerator is greater than the degree of the denominator. Okay, so you can see the degree of the numerator is 3, the degree of denominator is 2. That's when you have end behavior that is unbounded. There is no horizontal asymptote that the end behavior of that function is approaching. So your limit to infinity or negative infinity will either be infinity or negative infinity, but you have to think about it a little more deeply. So for example, I mentioned up here that the end behavior, I can ignore that plus 1. It had no impact on this function's end behavior. Okay, it means something, but not for the end behavior. So if I have, in this case, the 3x cubed that tells me the degree of the numerator and the x squared that tells me the degree of the denominator, that plus 1, I can just ignore that while I'm finding the limit to infinity. So I just simplify it down to the degree making terms of the numerator denominator, simplify it. Okay, well what it simplifies to is 3x, which is a linear function. It's a linear function with a positive slope, which has this end behavior. So the limit as x approaches infinity for this function would be infinity, because that's the end behavior of this linear function that it was simplified to. The limit to infinity as x approaches negative infinity of this function would be negative infinity, because this linear function that has a positive slope has end behavior that goes down to negative infinity on the left. All right, so let's look at some examples. All right, so rule number 1, the degree of the numerator is 2, the degree of the denominator is 3. If the degree of the numerator is less than the degree of the denominator, your limit to infinity is 0. And just like before, you should always answer with a complete limit to infinity statement. Number 2, this is rule number 2. The degree of the numerator is the same as the degree of the denominator. I'm going to isolate just those terms, simplify, and so my limit to infinity for this function is 2/3. Number 3 is rule number 3. The degree of the numerator is greater than the degree of the denominator. Again, I'm going to isolate the terms that got me the degree of the numerator and denominator. I'm going to simplify it. Simplifies to 5x. That again is a linear function with a positive slope, which has this end behavior. So if the limit is going to infinity, I'm looking over here, and that's going up to infinity, which was my answer. If this had said the limit as x approaches negative infinity, I would have looked down here, and my answer would have been negative infinity. So you will have to pay attention for limits to infinity. Is it going to infinity or negative infinity for a rule 3? Number 4. This is a rule 2. The degree of the numerator is equal to the degree of the denominator. So I isolate those terms. That simplifies to 1/2. That's my limit. For number 5, you could make it more complicated and find a common denominator and subtract to get a single fraction, and then it would just be one rule. Or you can separate the two fractions into separate rules. So x over 2, that's a degree of 1 over a degree of 0. So that's a rule 3. This is a linear function with a positive slope of 1/2, which has this end behavior, and x is approaching negative infinity, so I'm looking down here, and that part of it is negative infinity. This part is a rule 1. It's a degree of 0 over a degree of 3. So a rule 1, the limit to infinity or negative infinity is 0, but negative infinity plus 0 is still negative infinity. You would have gotten the same result if you had found a common denominator, subtracted the fractions. You would have still had just one rule 3, and you would have gotten the same answer. All right, number 6. So this is like the last example we had on the notes where the minus x does not have any impact on the end behavior of the function, so that can be ignored. I can simplify the square root of x squared into plus or minus x. But this is a limit as x approaching infinity. So I just want the plus x part. I don't need the minus x. So it's x from the top over positive x from the bottom. That is simplifies to 1. For number 7, same thing. I can ignore the minus x. So the bottom, the square root of x squared, simplifies to plus or minus x. It's still a rule 2. The degrees are the same on the numerator and denominator. X is going to negative infinity. So on the denominator, I want to use the negative x, and that simplifies to negative 2. So that's your answer. Number 8, so your limit as x approaches infinity of sine x over x is 0. So remember, this is just a shortcut. It's not mathematically the way it works, but if I extract out that sine x over x, and when it's going to infinity or negative infinity, that equals 0, and then times 2 is still just 0. It's not a rule. That's not one of your rules because there's not a degree to worry about. For number 9, again, if you want to find a common denominator and add, there'll only be one rule. But just like before, when we had a limit as x approaching some constant, the limit as x approaches either infinity or negative infinity of a constant is still that constant. So there's no rule there. That just equals 4. This is a rule 1. The degree is 0 over degree of 1. So that equals 0, and 4 plus 0 is 4. Number 10, this is a rule 2. Everything's not always in order, so you're looking at the negative 2x over the positive 3x, so the degrees are equal, and that part simplifies to negative 2/3, and that's your limit. Number 11, this is a rule 3. We're just using the 4x cubed over x squared. Those are the terms where we get our degree, and that's the part that's important for end behavior. That reduces to 4x. It doesn't always simplify to a linear function, despite our examples. But again, it is a line with a positive slope, and since x is approaching negative infinity, I'm looking on this end of this linear function that we simplify to, and my answer would be negative infinity. And last example, rule number 1, so you would look at the negative 2x, which has a degree of 1, and the 3x cubed, which has a degree of 3, and that's a rule number 1. So your limit to infinity, or negative infinity, in this case negative infinity, is 0.